For decades, air combat has been explained the same way. Stealth, speed, pilot skill, missiles. But what if the real battle was never in the sky? What if it was happening inside factories, crystal by crystal, wafer by wafer, long before any jet ever took off? Because the most disruptive shift in air warfare right now isn't a new fighter. It's not a new missile. It's a material transition, one that almost nobody outside defense engineering talks about. And if recent reports are even partially accurate, China may have just crossed a line the United States spent 20 years defending. Not with a new aircraft, but with a new radar material. Let's start with a rule that quietly governs modern air combat. Whoever detects first, targets first, shoots first. And in the age of long-range missiles, first shot usually means last shot. Dogfights are rare. Visual range combat is a fallback. Modern air dominance is decided tens, sometimes hundreds, of kilometers away, which means radar performance is no longer a supporting system. It is the weapon. For the last 2 decades, the gold standard for fighter radar has been gallium nitride, often shortened to GaN. GaN radars run hotter. They push more power. They see farther. They cut through jamming better. And that's why only 2 countries on Earth have mastered GaN radar at scale: the United States and China. Not Europe, not Russia, not Japan. Just 2. This isn't about intelligence or design talent. It's about manufacturing brutality, the ability to refine, process, and mass-produce exotic materials that have almost no commercial market. Gallium nitride isn't used in phones. It isn't used in cars. It isn't used in consumer electronics at scale, which means no profit incentive. Only states with massive defense budgets and complete industrial chains can justify it. That's why the F-22 and F-35 use GaN, and why aircraft like the Rafale still rely on older gallium arsenide technology. Now here's where the story changes. Because gallium nitride may no longer be the ceiling. The material quietly being discussed now is silicon carbide. And this isn't a minor upgrade, it's a different class of physics. Silicon carbide can operate at higher temperatures, higher voltages, and higher power densities than gallium nitride. In radar terms, that translates to longer detection range, sharper resolution, faster target discrimination, better resistance to electronic warfare. In simple language, it lets a radar see farther, clearer, and through more noise, all at the same time. If GaN was the leap from 4th generation to 5th generation sensing, silicon carbide is the step beyond that. This is why the rumors matter. Not because of hype, not because of national pride, but because if even a portion of China's J-20 fleet transitions to silicon carbide radar, the engagement geometry against aircraft like the F-22 and F-35 changes, not slightly, fundamentally. The aircraft that sees first sets the rules. The aircraft that locks first controls the timeline. The aircraft that launches first forces the opponent into defense or destruction. And stealth alone cannot solve that. Stealth reduces detection range. It does not eliminate detection. At sufficient power and sensitivity, stealth becomes delay, not immunity. To understand why this matters, we need to look at something most discussions ignore: industrial stamina. The United States pioneered 5th-generation air combat, but it also made a strategic decision that now haunts it. It stopped producing the F-22. The production line was shut down. Suppliers disappeared. Tooling was dismantled. Today, keeping the F-22 operational often means custom manufacturing parts that were once mass-produced. That's why readiness rates have struggled. Not because the jet is bad, but because the ecosystem around it is gone. The F-35, meanwhile, is produced in large numbers, but across a sprawling multinational supply chain with persistent maintenance and availability challenges. Now contrast that with China. China didn't just build a jet, it built an industrial loop, Large fleets, continuous upgrades, shared subsystems across multiple aircraft types, and manufacturing lines that never stopped moving. The J-20 isn't a museum piece. It's a platform. This is where materials matter more than marketing. Advanced radar materials don't come from labs alone. They come from refining capacity, crystal growth facilities, semiconductor fabs, precision machining, and honestly, brutal cost tolerance. China possesses the world's most complete industrial system. Now, that doesn't mean everything is superior, but it does mean iteration is faster. When a breakthrough happens, it can move from experiment to prototype to deployment with less friction. And that's exactly how material advantages compound. Now let's talk about something uncomfortable. The United States absolutely has the scientific ability to develop silicon carbide radar. That's not the problem. The problem is cost asymmetry. Advanced manufacturing in the US is expensive. Labor is expensive. Compliance is expensive. Supply chains are fragile. Every step costs more. Meanwhile, China can absorb long development cycles because it treats strategic industries as national infrastructure, not quarterly profit centers. That difference doesn't show up in press releases. It shows up 10 years later when one side can afford to deploy upgrades at scale, and the other can't. There's another layer most analyses miss. Materials don't just decide performance, they decide tempo. If one side can upgrade radars, electronics, and sensors faster than the other can respond, air dominance becomes temporary, constantly shifting. And that, honestly, forces the opponent into permanent catch-up. This is exactly how the Soviet Union was pressured during the Cold War. Not through one decisive weapon, but through endless technological pursuit. The cost wasn't defeat in battle. It was exhaustion. This is why radar materials matter more than dogfight videos. Because honestly, air superiority today isn't about one jet versus another. It's about who upgrades faster, who fields changes at scale, and who can afford to keep pushing the ceiling. And materials sit right at the center of that equation. Missiles change, airframes age, engines wear. But a sensor advantage reshapes every engagement downstream. Now zoom out. This isn't only about fighters. The same material ecosystem supports electronic warfare systems, early warning aircraft, naval radar, missile seekers, and space sensors, which means a radar breakthrough doesn't stay in one aircraft. It spreads, quietly, relentlessly. So what does this mean right now? Well, it means the competition is no longer just about who has the best jet today. It's about who controls the next material bottleneck. Gallium nitride was one such bottleneck. Silicon carbide may be the next. And honestly, history shows that when one side gains material dominance, catching up takes years, not months. Here's the final takeaway. Air superiority is no longer decided on runways or in dogfights. It's decided in furnaces, in fabs, in factories most people will never see. If the J-20 truly transitions to silicon carbide radar, even partially, it doesn't mean instant dominance, but it does mean something far more dangerous. It means the race just moved again, and one side may already be running on a different surface. And in modern warfare, the side that controls materials controls the future. That's why this matters now.